Hello everyone, my name is Abhishek Jain and my branch is Electronics and Computer.
Hello everyone, my name is Sanyam Rastogi. My branch is Electronics and Communication.
Hello everyone, I am Namit Joshi from branch Electronics and Communications Engineering.
Hello everyone, my name is Ravisha and my branch is Electronics and Communication.
Hello everyone, my name is Archit Anurag Kaushik and my branch is Electronics and Communication.
Hello everyone. So our project aims at designing and implementing a floating point multiplier and an adder subtractor unit on a Xilinx Zinc UltraScale Plus platform. Main motive behind choosing this project is to learn various designing aspects of digital VLSI design and the ways in which the design can be verified and synthesized using a particular tech node. Okay, now we'll talk about the IEEE 754 standard, which is used for representing the floating point in binary. Okay, the 32 bits are divided into 3 fields. 31st bit is a sign bit, there is an 8-bit exponent, and the 23-bit mantissa. The bit stores a value 0 for positive number and 1 for negative number. The exponent is stored in excess 127 code. The implicit bit is the most significant bit that is not contained in the 23-bit mantissa, which is actually a 24-bit mantissa. Okay, now we will talk about the steps which are used in addition and multiplication process. First, in addition, we check for zeros, then we calculate exponent difference, then pre-normalization is done in which the small floating point operand is adjusted in order to align the two floating point numbers. The next is addition and subtraction. The second last step is post normalization, and the last step includes a rounding. Similarly, in multiplication, the first step is to check for 0. The second step is to determine the resultant exponent. The third step is to multiply the mantissa. The fourth step is normalization. The resultant mantissa is normalized and the consequent exponent is modified in this step. And the last step is rounding. Okay, now we'll talk about the 24-bit adder architecture that we have created. We researched about various adder architectures and arrived at a conclusion that a parallel prefix adder using Link's carry equation will be suitable for 32-bit floating point adder, which can be both high speed and low power. Okay, these odd and even prefix tree are shown on the screen and they are created as a separate entity, and a 24-bit adder is created out of this. This 24-bit integer adder design is used to carry out the addition process in the big ALU part of this FP adder hardware flowchart. Similarly, various multiplier architectures were also studied. For example, the Vedic multiplier, Booth-Wallace multiplier, the Wallace tree multiplier, and we arrived at a conclusion that a Vedic Wallace multiplier will be suitable, and so we created a hybrid of Vedic Wallace 24-bit multiplier as shown in the figure. The process which was used to create this multiplier, and then this 24-bit integer multiplier design is used to carry out the multiplication process in the 24-bit multiplier part as shown in this flowchart of the 32-bit floating point multiplier architecture. All the details regarding the architecture of both the units are mentioned thoroughly in the report. We functionally verified both the units using Xilinx Vivado on a Zinc UltraScale Plus platform. As you can see, both the simulation waveform for both the units is present on the screen. The critical path delay for the adder came out to be around 3 nanosecond, and for the multiplier it came out to be around 11 nanosecond. And the clock used for designing for both the units is 50 megahertz. Now have a look at the code. So here is the overview of the adder. We have used a Zinc UltraScale plus ZCU106 evaluation platform for synthesis. This is the top module code of the adder, and now we are going for this to run the behavioral simulation. So this is the functional simulation of the project. Adder, 32-bit adder, floating point. Yes. And here is the functional simulation for the multiplier.